Okay, so to do this one, wow, that doesn't seem very zoomed in. Can you guys, hold on. So anytime you do absolute value and you're solving an equation or an inequality, you're going to set it into two separate equations. Okay, so you do a positive version and then you do a negative version. So your positive version is exactly the same without the absolute value, and then your negative version is exactly the same except for first you switch the sign and then you make the other side opposite. Okay, and then you just solve those two individually. Okay, so you would add 13, so that makes 23, divide by 2. So that would be one solution, and then if we add 13 over here, what's that? Only if you divide by a negative. Multiply or divide by a negative is when you flip. So the second solution is 3/2. Okay, so once I look at these two scenarios, I have x is greater than 3/2 and x is less than 23/2. Okay, so that's going to be is that an and statement? Did I do that right? Yeah, so it's going to be, yeah, 3/2 is less than x is less than 23/2. So it has to exist in between, whoops, 23/2. There we go. It's getting intense over there. Okay. So how to graph these? This is from the first section. Do you guys remember what happens if you have a negative on the outside of any function? What does it do? Flips it upside down. So all we're going to do is draw that shape flipped upside down. Okay, so if we have like doom.
Yeah, sure. Well, I just haven't warmed up yet.
Okay. How'd you do B? If you have an x on the inside, how does that change? It's a reflection over the y-axis. Okay, so for B, we're going to reflect over the y-axis. Okay, so basically those spots that I just kind of drew as reference points go to the other side. Like that. Okay, what about C? If I have absolute value, what happens? Everything goes what? Above. So I basically reflect everything above. So there is a little hump that is already above. That piece stays exactly the same, but anything else gets reflected above. So then this would look like that. Okay, so D is the hard one. Does anybody remember how to do D? When you have absolutely... Okay. Yeah, you're right. Okay, so basically you just take everything that's on the right-hand side, so everything that's in the positive of the y, and you draw that. Okay, so you're looking at just this right-hand side. And then you also draw the left-hand side, which is a reflection of that over the y-axis. So that might be something you might want to write in your notes, like how to draw that. Give yourself some words as to how it's done. How would you put that in words? I would say draw everything that's on the positive side of the y-axis. Then reflect that over the x-axis, and then give yourself an example of it. Yes, John? One page of notes.
Positive side of the y-axis or reflected of x-axis?
No, over the y. So you just draw the positive side of the y, and then once you draw that, you take it and reflect it over the y-axis. So that left-hand side is a reflection of the right-hand side. So it's always going to look like a reflection over the y when you're finished drawing. It'll always be a mirror image. Okay, even, odd, or neither. How do I decide if something is even, odd, or neither? There's two ways I can go about this.
Even.
Okay.
The exponent.
Kind of. I wouldn't say necessarily the exponents. That does absolutely help. Okay, so question number 4, which one do you think it could be?
Even.
It could be even. Now, it's not necessarily true that that will always be, just because it's squared, potentially even. It is possible for an x cubed to be even. And actually, one of the problems on this assignment that you have to draw is an even function. And I'll show you, we'll get to that one.
Well, how do you know then?
So the best way to tell is if you plug in a negative x. Okay, so if you plug in a negative x and simplify and it comes out exactly the same, that's even. If you plug in a negative x and it comes out exactly opposite, like everything is negative, that's going to be odd. Okay, so if I plug in a negative x into this x to the 4th, is it going to stay exactly the same? Yeah, it is going to stay the same because both x's are squared, so x squared is going to cancel out a negative. This is going to become an even function. Okay, so you can also just type these into the calculator and look at them graphically. Remember, even is a reflection over the y-axis.
Odd is
And odd
over
is
the origin.
over the origin.
X or Y. And then neither's if it's
Over
like
the y-axis, or the origin. There's nothing over the y.
I thought Y axis was odd or even. And I thought the X axis.
Oh, y-axis is even. Sorry, I said that. So even is y-axis. Nothing is over the x-axis. Okay, so what about number 5? Potentially odd, but is it odd? It's not odd because of the -1. Because if I plug in negative into that, it becomes negative x to the 5th minus 1, which is not exactly opposite. For it to be exactly opposite, it would have to be negative x to the 5th plus 1. Every term would have to be opposite. So this is a neither.
Oh.
Okay? And graphically, it looks like a John Travolta that has been moved down 1 unit. It does not cross through the origin. It is slightly shifted.
So when it's neither, it's just like you plug it in and it doesn't completely change, but it sort of does.
Right. Mm-hmm. Okay, how do I do the domain for this one?
You have to see what the denominator can be.
Okay, so what can the denominator not be?
Negative number or 0.
Or 0. Okay, good. So we would have to say that the x has to be greater than 0. You could also write that in interval notation. And you'd have to say 0 to infinity. We want to make sure that you do not include 0, though, because 0 would make it undefined. Okay, how would we do range?
You switch the x equal y's, right? Or no?
Well, the the ranges of the y values. I think the easiest way to do this is to graph it. Type it into the calculator and see what it looks like. Okay, so let's do it. How far down and how far up does it go? So if you hit alpha window, that's your absolute value. So we have of x divided by the square root of x. Let's zoom 6 because I don't know where I was before. Okay, so it's just the top half of kind of like a parabola that's on its side. What's my range?
0.
Do I include 0? Does it actually touch 0?
No.
No. Okay, so my range for this one is the same as my domain. So 0 to infinity. Okay, Number 8, this time we're going to infinity. So if we have a limit that's going to infinity, what are we concerned about? The exponents. The end behavior. Is it bigger on the top? Is it bigger on the bottom? So what is my biggest exponent on the top? And what's the term in front of it? Or the number?
Yeah.
2x squared, right? Because you have to FOIL it.
Okay, so if you FOILed it, what would the first term be? X to the 4th, right? 4x to the 4th. So you'd get 4x to the 4th if you FOILed that out. So notice that you have a 2x on the first term, and a 2x being squared is 4x squared. Okay, and then you have times 2 more x's, so it's 4x to the 4th. Okay, on the bottom I have an x to the 4th. Okay, so where's my end behavior? What do we have? Do we have a horizontal asymptote?
4.
At 4. Okay, so this is the scenario where it's the same, x to the 4th over x to the 4th, so you're looking at the values that are in front of those. So you got 4 over 1. So this is going to 4. Okay, in both directions and back. Okay, what about question 9? How do I do this one? This one is going to -1. What do I do? Okay, so if I plug in -1, I end up with 0 over 0, which is a whole, so that means the limit exists. So how do I do it? What?
X plus
Break it down. Good, I got a factor. Okay, so it's going to be x plus 1, x minus 1 over the x plus 1. So those would cancel. Technically, I should be writing limit as x approaches -1 when I do that. Okay, that's something that they would take points for on the AP exam. Okay, keep your notation. Okay, and at this point now we would plug the 1 back in, or the -1. Now that's when just factor the top, x squared minus 1. So now when I plug it back in, that's when I lose my limit notation. Whoops, I guess I need to say equals. So what's -1 minus 1? -2. So that's what my limit value is. Number 9. That's number 9.
So when it's the limit is to infinity, it's bigger on the top. If the exponent, it's 0, right?
If it's bigger on top?
Yeah.
No. Bigger on bottom is 0.
Okay.
Bigger on top is the one that goes to infinity or negative infinity. So you have to plug in infinity to see where it's going.
And that's where the horizontal asymptote is.
Mm-hmm. Yep. Okay, what about question number 10? So again, the idea, if I'm given a number, I would plug it in. What happens if I plug it in? I get 0 over 0. Okay, so this is one that I have to kind of think about more graphically because there's nothing I can do to manipulate this equation. I can't factor, I can't cancel it out. So it's going to be valuable for this one to graph it, okay, and see what's happening at -1. Okay, so if I type this in, if you type it in, no, because it's going to be a oh, I see what you're saying. Yeah, but it's going to be it's a step function. Because see how it's, well, wait a second. Over 0 though, right? Over 0. So if you get a number over 0, what's your likely answer? No. Undefined is what's happening. A step or potentially a vertical asymptote. A lot of times it would be a vertical asymptote. Okay, so that's going to be a does not exist case. Okay, so what's happening at -1? Doesn't exist. Okay, there is a vertical asymptote. Okay, So this is a does not exist. Okay, here comes this A and B scenario again. Okay, so this one is talking about the idea of continuity. So we got a piecewise function that is continuous. Okay, so it's basically saying this top piece is going to connect to this piece at the same y value. What is the x value that they're going to connect at? At -1. Okay, so that is information right there that we can use. Okay, so I can start by plugging the x value in to my middle piece because I have more information in that piece, and figure out what the corresponding y value is and set that equal to the top piece. Okay, so if I take 2 times -1 minus 3, what is the corresponding y value at that spot? -5, good. Okay, so then I'm going to go back to the top piece, and since they must be going to the same place, I'm going to say, well, -5 has to equal that top piece where the x value is -1. Okay, so I'm going to say -5 is equal to a times -1 plus b. Okay, so that gives me this scenario of I have two unknowns. I don't know what my a or my b is, so I'm probably going to have to do a substitution. So I want to solve for one of these variables. Which one will be easiest? A? You want to solve for A? I feel like B, but okay, A. Barron says so. So then A would be B plus 5, right? Because you'd add the A and then add the 5. Okay, so now let's look at the bottom piece. Okay, so the same idea. We have the middle piece has to be the same as the bottom piece at that point. What's the x value that we know is true? Okay, at 3. Okay, so we can take that middle piece, plug 3 in to find the corresponding y value. So what's the corresponding y value at that spot? 3. Okay, so we're going to do the same thing. We're going to set the bottom piece equal to 3 at the x value of 3. Okay, so you got the same situation here. We've got an a and a b that we cannot solve for, so we can do a substitution. You want to throw it in right now? Or should I do a little more simplifying first? What makes you happier?
Right now.
Throw it in right now?
Yeah.
And just go for it? Okay. So can I just say, I'll just simplify 3 squared is 9, so we got 9b minus 3, and then my a, we substitute in b plus 5. So we got 10 b's on the right-hand side, and we've got plus 2. So if I subtract 2, can we all agree that I have 1 on the left-hand side? Is that okay for that mental math? You guys follow it? Okay, so then I just divide by 10, so b is 1/10, which is yucky, but true. Okay, so then I have my b value. How do I find my a value? Right. So a is b plus 5, so b was 1/10. 5 is the same as 50/10. So what's the a value? 51/10, good. Ew. Okay, so here's one of your favorites. Okay, so first we're going to come up with all this good information on the left. So it starts by asking us about the domain. So how do I figure out what the domain is?
You see if as you take to make the bottom bigger.
Okay, so what should I do? So let's start by factoring the bottom. What can I pull out? 4x. Okay, so if I pull out 4x, I'm left with x squared minus 4. And can I factor that further? Can I factor x squared minus 4? To x plus 2 and x minus 2. Okay, so what is my domain restrictions? X cannot be what?
0.
Can't be 0, can't be 2, and it can't be negative 2. Okay, the next thing it asks us to do is to reduce. Okay, that means that I need to factor the top and see if anything cancels out. Okay, so what can I pull out of the top? I kind of do this off to the side.
X.
Pull in x, so I have x, and then I have x squared minus 1, which I could factor, but I don't find that helpful if I factor that because it would just be x plus 1 and x minus 1, and that's not going to cancel with the bottom. Okay, so what does cancel? An x.
If you pull out an 4x.
On the bottom, yes. Okay, so my reduced function is x squared minus 1 over x plus 2 and x minus 2. Okay, so that tells me that I have 2 vertical asymptotes. Where are the 2 vertical asymptotes?
Where did the 4 go?
Oh, I meant to say 4, sorry. Just kidding. So where are my 2 vertical asymptotes?
0.
At 2 and negative 2. Okay, so that's what's left. So if once you reduce, and anything that makes the denominator at this point, that's where vertical asymptotes are. Okay, so we have vertical asymptotes at x equals plus or minus 2. Okay, do I have a hole? Yes, hole at 0. Okay, and just so you guys know, in the past I've just kind of said at x equals 0. It is possible for you to find the corresponding y value, find the exact point where the hole lies, okay, by simply plugging the x value of 0 into the reduced function. Okay, so if I plug 0 into the reduced function, what would I get for the corresponding y value? Hi, Matt. Well, we were doing good until you came and interrupted us. Oh, thanks. -1 over -16. So a positive 1/16, right? So 1/16 exactly is where that hole will lie. Does that make sense? So, no, in my opinion, you do not have to, but I think that it's valuable in helping you draw the function. Because if you have another point to kind of draw your function through, even though it's technically a hole, that helps you figure out where the function is. So I think that's valuable. Okay, so x-intercepts. Where do you find the x, or how do you find the x-intercepts? Nope, wrong side. X-intercepts is if you set the equation equal to 0, so you're setting the top equal to 0. So if you set the top equal to 0, what do you get? 1 and -1, right? Plus or minus 1. You guys follow that? Top equal to 0? Because you would add 1, square root it.
Yeah.
Square root of 1. Okay, y-intercepts is if you set the x equal to 0, technically what is happening at your y-intercept, which is the x value of 0.
It's a hole.
It's a hole. So technically there is none. Okay, it is a hole. Even though we can kind of say it, the function looks like it crosses through at 1/16. On the calculator it'll look like that. Okay, horizontal asymptotes, that's end behavior. If we go back to our original, is it bigger on top, bigger on bottom, or is it the same? Same, so where's my horizontal asymptote? 1/4, good. So y equals 1/4. Okay, so symmetry. If I plug in a -x into this original function, what happens?
The signs will all change.
All of the signs would change. So therefore, what kind of function is it?
It's not a function.
Oh, yes, it's a function. It's a So even, odd, or neither.
It's an odd, right?
It's an odd function. Or excuse me, no. It's an even function.
I thought it was when they changed it all at once.
So because what happens if all of the signs change, right? You basically have a negative over a negative, right? If you pull them all out, they all change. Do you see what I'm saying? Let me do it. So if I have negative x cubed, oh, hold on, I need to technically write this outside. Cubed, is it minus? Minus negative x over 4 times negative x cubed minus 16 times negative x. Okay, so it basically turns into negative x cubed plus x over negative 4x cubed plus 16x, right? And then if you pull a negative out of the top and the bottom, negative x to the third minus x over negative 4x to the third minus 16x, what happens? Yeah, it goes back to the original. So this is one of the very, very, very few instances where you have basically a cubic, but it is in fact an even function. It's symmetrical over the y. Okay, just because of the ratio, the fraction. Okay. All right, so let's draw this sucker. So we got asymptotes we can draw. So we got -2 and +2. We have a horizontal asymptote at 1/4, so right about there. Okay, my whole is going to be helpful, I think. My whole is at 0, 1/16, which is just slightly above the x-axis, so it kind of is like right there. And then I have my two x-intercepts, which are at 1 and -1. Okay, the other piece of information that is valuable when you're graphing is your vertical asymptotes, knowing if they're even or odd. Okay, what kind of vertical asymptotes do I have? Do you remember where I'm looking for that? I'm looking at my reduced function, and I'm looking at the exponents. Are they even or odd exponents for the x plus 2 and the x minus 2? They're both odd. Okay, so remember the difference between an even asymptote and an odd asymptote? Do you guys remember? Okay, so an odd exponent, the asymptotes, the function is going to split apart like that. Okay, an even exponent, they're going to ride the same asymptote line. So they're both going to go in the same direction.
And how do you figure that again?
Just by the exponent. So I'm looking at my reduced function, and I'm looking at the exponents here. So if this happened to be x plus 2 squared, I would have kind of like that volcano effect. So either they're both going up or they're both going down, as opposed to going in opposite directions.
But isn't the bottom they are?
No, because you're looking at each linear quantity separately. If you FOIL it, you're taking away the two different, because it's two different spots, right? There's a 2 and a -2. If you FOIL it, you're like going backwards, putting it back into standard form. Okay, so when I draw this, in the middle, what I see is basically it looks like a parabola. Okay, I know that that's going to go down and it's going to hug and get infinitely close to this asymptote. So it's basically just a parabola here. Okay, so then I know on the other side, so if I'm looking at the right-hand side, since it's an odd vertical asymptote, it's going to start in the opposite direction. I don't have a point to cross through, but I know it's going to fall towards the end behavior. So it's going to close close to that asymptote, the horizontal one. Okay, the left-hand side is really going to do exactly the same. Okay, so that kind of looks like a really sad face. Does that make sense on how to draw that? That one wasn't too hard. Okay, and you can see the even symmetry. In my opinion, I don't think knowing that it's even or odd is incredibly helpful, but maybe to a small point.
Wait, so even symmetry, they cross over the y and odd
Symmetrical.
symmetry, they cross over the x versus
The y
origin.
equals the origin. The y equals x line. Ah, okay, here's one that comes back from the dead. By using the limit definition.
Oh,
You guys remember what the limit definition is?
it's like you have the-
Nice. So it's limit as h approaches 0. Don't forget that part because that's technically important. You would lose points on a test if you didn't write that. The f of x plus h minus the function of x all over h. Okay, so that might be something you put on your notes and maybe even give yourself an example that you can use. You can't remember that. Okay, so if we plug in our f of x, okay, the first step is plugging in x plus h into the x. So we're going to have 2 times x plus h squared minus 1. Then I'm going to subtract my function of x. So minus, make sure you use parentheses, 2x squared minus 1 all over h. And at this point, that's really, I think, the hardest part of all this. Now you just simplify, and it
So
should just
what's
pop
that? Is
out.
that
You
first
know,
one, the equation?
yeah, that's just the equation. So this is the part, I would write this down in my notes somewhere, probably, for the test. Write it as limit definition, label it so you know what it is. All right, so can I go ahead and FOIL and distribute a 2 at the same time? Would that be too crazy? Okay, so you'd have x squared for your first term, so you have 2x squared. The middle term is 2xh, so if I take 2 and multiply by 2xh, that's 4xh. Third term is x squared, so I multiply that by 2, so 2h squared. So then I got that minus 1 at the end. Distribute the negative through, so I have minus 2x squared plus 1 all over h. Okay, so then I'm looking at things that cancel. Does anything cancel? 2x squared and the 1s. Good. Okay, so what should always be left when you're doing the limit definition? Every term on the top should have an h in it. Okay, so my next step is going to be to pull an h out of every term on the top. So I would have h and then 4x plus 2h over h. And what does that allow me to do? Cancel the h's. And now once I cancel the h, I'm going to take the limit. So I'm going to plug 0 into the h. Okay, so this is where I lose my limit notation because now I'm actually taking it. And then I simplify. Okay, so the nice thing about this is you know the answer because if you just did the basic differentiation method and derived that originally, it would just be 4x. So you know what the answer is, right? There? Okay. So question 19 kind of does, this is really a big idea here. Average rate of change and instantaneous rate of change. This always keeps coming back. How do you find average rate of change?
Take the derivative.
No,
No, that's
instantaneous.
You just plug it
Good. You plug your x values in, so you're just doing slope formula. That's for average rate of change. So we need our corresponding y values. Okay, so we're going to figure out what f of 1 is equal to. Okay, so what's f of 1's value? 0. And what's our f of 10 value? So it would be 10 minus 1. Sure. So 3 for that one. Okay, and then we're just going to do the y1 minus the y2. So 0 minus 3. And then the x1 minus the x2. So we get negative 3 over negative 9, which is 1/3. Okay, so instantaneous rate of change, how do I do this one? If they give me a t-value of 5. Very good. Okay, so I'm just going to derive it. So the first thing I want to do is rewrite this one. So this would be the same as t minus 1 to the 1/2. So what's the method that I need to use in order to derive this? Not quotient, chain. Yeah, so you do the derivative of the outside times the derivative of the inside. So 1/2 times t minus 1 to the negative 1/2. And then what's the derivative of the inside? It's 1. So I'm not going to say times 1. That's okay with you guys. So this would be the same as 1 over 2 times the quantity of 1 minus t. No, I said that backwards. T minus 1 to the 1/2. Okay, so there's your instantaneous rate of change at any point. So what do I do with the 5 now? Plug it in. Good. So I can say the first derivative at 5 is 1 over 2, 5 minus 1 to the 1/2. So 5 minus 1 is 4, the square root of 4 is 2, and 2 times 2 is 4. Good there? Okay, question 20. So here's a, what do you guys, when you look at this, do you go, uh-oh, does that look hard?
Yeah.
I kind of think that too, but then I read it and it's actually super easy. So they give you this equation, which is representing the volume of a Q, and they simply ask you to find the rate of change, which is just saying find the first derivative in terms of E. Okay, so that basically means every variable that you drive, you need a dx, dE, dy, dE at the bottom. Okay, in the past we used dx. This time we're using E. So what's the derivative of the V? Not 0. Technically 1, right? The derivative of V is 1. So it's 1 dV dE. So you have to write it in that notation, dV dE. Okay, and then you derive the E cubed. What's the derivative of E cubed? 3E squared. And I would, at that point, say, since I derived an E, dE dE. Do I need to say dE dE? That's 1, right? Okay, so you don't need to say if it's in terms of its own variable. That's why we never wrote the dx dx before. Okay, so there's your first derivative. Then it says when E is 10, so what are you going to do? Plug in 10, exactly. So you just plug it in, and you do, yeah, you get 300. So 300 is the answer. Okay. So really, it's actually a very simple question, I guess, as long as you understand it. All right, so here's 21. This is where things get more fun. This is a little more fun. This one's not really that hard. So we're just doing implicit differentiation on this. Okay, so we got the first term, x squared times y. So how do I derive that?
Yeah, 2x and then y times y derivative. Right?
No, you got to do product rule. So this piece, we got two variables that are being multiplied. You got to do product rule. So you have to do first d second plus second d first on just that piece. So you have first x squared d second. What's the derivative of y? dy dx. Plus the second, which is y, times the derivative of the first. Okay, so what's the derivative of x squared? 2x, and then we would technically say dx dx, but we don't need to say that because dx dx is 1. I'm going to use parentheses so you are clear that that's that first piece. Okay, what do I do on the 3xy?
Product rule again.
You got to do the product rule again. So I'm going to separate the 3. If that's okay with you guys, I'm going to pull the 3 and just do product rule between x and y. So x times y. You can group the 3 with the x if you want, if that makes you feel better. That would be the same thing. But I'm just going to pull it. I don't know, for me it just seems easier. So I'm going to do x and y. So I have first, which is x, and then the derivative of y.
Just dy dx.
dy dx, good. Plus the second, so y, times the derivative of first. What's the derivative of x?
1.
1. Okay, so now we're on the third term. What is the derivative of y cubed?
3y squared dy dx.
Good, dy dx, good, don't forget that. And then on the other side, what's the derivative of 10?
0.
0. Okay, so now at this point, all you have to do is set it all equal to dy dx. So I'm going to start by distributing, getting rid of my parentheses, and then I'm going to pull everything that's not dy dx to the right-hand side. So I have x squared dy dx plus 2xy minus 3x dy dx minus 3y's plus 3y squared dy dx. Okay, so now I'm leaving all the dy dx terms on the left-hand side. Everything else is getting pushed to the other side. So I'm going to have x squared dy dx minus 3x dy dx plus 3y squared dy dx. That will equal negative 2xy plus 3y. Okay, so on the next step, I tend to just kind of do 2 steps in one. If I pull out a dy dx, my next step would then be to divide by that what's left over. Can I do 2 steps in one and just divide it straight to the other side? Does everybody follow that? I just don't want that to be confusing because that can be a very confusing step. So you'd have negative 2xy plus 3y, and then you divide by all of the things that get left over.
Okay.
So you have...
But my question has always been, like, what happens, because there's, like, 3 different dy dx over there. Do they just combine?
You're pulling it out like a greatest common factor. So you're pulling all 3 of those out.
Okay.
So there's technically only one when you pull it out as one greatest common factor.
It's math.
Right. Distributive property. Good there? Okay. This one, I feel like I've seen this one before. It keeps coming back.
It's because I'm the one I always get stuck on.
Yeah, this is the same one. Okay, so we're finding the equation of the tangent line that's parallel to the other one. So what do?
You have to set the slope of this equal to the slope of that.
Set the slope equal to the other slope. So how do I find the slope of the first line?
Well, I don't know.
How do you find slope of any equation? The first derivative. Good. Okay, so I'm going to take the first derivative, and then I will set that equal to the slope of the other line. So I kind of wish they used a different y, but that's okay. So we got x to the 2/3, so the derivative of x to the 2/3 would be 2/3 x to the negative 1/3, right?
Yeah.
Okay, which by the way is equivalent to 2 over 3x to the 1/3. Okay, so now since I know the slope that I want it to equal, I'm going to set it equal to what slope? 1/3, good. So I'm going to have 1/3 equal to that first derivative, so I can figure out exactly what x value that slope is equal to 1/3. So I'm going to cross multiply since I have a ratio set equal to each other. It's going to give me 3x to the 1/3 is equal to 6. Divide by 3. And then last step to get rid of the 1/3. Cube both sides. So everybody follow that x is equal to 8. Okay, so I have a slope, I have an x. What's the piece I'm missing?
Intercept.
No.
Or B.
No, because I want to keep it in point slope form.
Okay.
Okay, so I'm missing the y. Good. So I'm going to plug my x into the original. So since my x is 8, I go back to the original, plug it in to figure out what the corresponding y value is. So what is that?
64 to the
4?
64 to the square
Cube root.
of the cube root. Yeah.
So 4, right? Okay, so my point is 8, 4. So my equation will be y minus 4 is equal to 1/3 times x minus 8. Okay, 22. So this one is very similar. We're finding the equation of the tangent line, although we don't know the slope this time. They give us the x value. And then they also ask us for the normal line equation. You guys remember what normal is, the normal line?
Isn't that the... I don't remember.
Perpendicular, very good. Okay, so all we're going to do, the two equations are going to look exactly the same except for the slope. The slope will just be a negative reciprocal. Okay, so how do I start this? If I'm finding the equation, I'm thinking about slope. How do I find slope? Derivative. What method do I have to use for this one? Quotient. Okay, so it's going to go ho d hi minus hi d ho. So my ho is my x plus 1. My hi derivative is 1 minus the hi times the derivative of the ho all over the ho squared. So we get x plus 1 minus x on the top, which is 1 over x plus 1. Okay, so now what? So what are we going to do with the when x is equal to 1 part? Plug it in, okay? So we're going to find the slope by plugging 1 in. So I'm going to write, oh, I forgot my y derivative notation. 1 over 1 plus 1 squared, so 1 over 4. Okay, so I have an x. This is my slope. What's the one piece I'm missing again? The y. Okay, so how do I find the y? Plug the x back in. So if I plug in, I'm just going to write this right here. Let's see, if I plug 1 in, I get 1 over 2. So 1/2 is the point we're looking at. So the tangent equation is y minus 1/2 is equal to 1/4 times x minus 1. Okay, so the normal line, all I need is the perpendicular slope. 1, the x that's given.
Oh, okay.
When x is equal to 1. So what's my perpendicular slope? -4. So I'm just going to change the slope on that. So -4 x minus 1.
So normal is just perpendicular.
Perpendicular, yep. Perpendicular to the tangent line. You guys ready for a break yet?
Yeah.
Should we take a stretch break? Okay, so this question 26 is one that I feel like you guys have kind of had some problems with, these rate of change questions. Okay, so let's see. So we have a circle whose radius is increasing at a rate of 5 inches per second. So right away, what is that? I'm going to say it has
That's a rate of change.
a rate of change. Okay, so it's a rate of change, so we can say that the dr dt, so it's a rate of change per time, and you can tell that by the way it's labeled, inches per second. Okay, so that's equal to 5. Okay, and it's also important that you note if it's increasing or decreasing. Okay, so if it was a decreasing rate, you would want to say it's a -5. Okay, so make sure you read that part carefully. So at what rate is the area of the circle increasing? When the radius is 7 inches. Okay, so right there, when the inches is 7 inches is an instantaneous rate of change. Okay, so we can say the r is equal to 7 at some point in time. Okay, that's given information. Okay, so since they're asking us to find the rate of change of the area, what are we going to do with that formula?
Derive it.
Derive it. Okay,
In
so
terms of
derivative
A.
finds rate of change. Well, technically in terms of time, because it's increasing in seconds. So I start with the A. What's the derivative of A if we're deriving it in terms of time? dA dt. So dA dt is equal to, now we're going to derive pi r squared. So what's the derivative of pi r squared?
Sorry, that's my phone.
2 pi r dr dt. Everybody okay with that piece? So again, driving it in terms of time. Okay, so now we plug in any given information that we know. So we're looking for the dA dt. The r was 7, and the dr dt is 5. So we plug that information in, and let's see, we got 35 times 2, so 70 pi. Okay, and then I want to make sure that I label this correctly. How would I label this? Inches per second squared. Very good.
Or inches squared per second.
Inches per second squared.
Inches squared.
Yeah, you're right. I do the inches. The inches is technically squared. Yes, you're right.
Not squared.
We're not squaring seconds.
So would that make it acceleration, or what would that make it? As acceleration.
No, it's
Second
velocity.
squared. Yeah. Okay.
It would be a velocity. Yeah, but if we derive that, then we would find an acceleration. All right, where are we at? Okay, so here's this stuff with concavity and such. So we got to use the number lines. First of all, we're going to figure out where it's increasing, decreasing, and could have a potential max or min. Okay, that's not too bad. So for question number 5, we go up, down, up. Okay, so where is this function increasing? Let's see, where should I write this? Right over here. 5.
From
A.
negative 2
-2.
and from 0 to
Okay.
2 billion beyond.
Okay, where is it decreasing?
-2 to 0.
-2 to 0. Good. Relative min.
0.
Okay, we want to say x equals 0. And relative max. 2. -2. Good. Nice. Okay, for 6, same thing. Okay, notice that this time it gives us a domain restriction. Okay, so what does that tell us if we have a domain restriction, potentially? There's an asymptote. Okay, so I like to draw the asymptote there, just kind of as a reminder. So we got up, down, up, down, up. Okay, so this would kind of look like, I don't know, the hourglass scenario. Okay, so A, where is it increasing?
2 to 0.
-2 to 0.
3.
it is decreasing.
The opposite.
Negative infinity to negative 2, and 0 to 3. Minimum.
Oh, it doesn't exist.
Minimum. Bottom.
Yeah.
Yeah, negative 2 and 3. Maximum. So what do we say? Doesn't exist. I would just say none. Or does not exist would be absolutely fine.
Minimum is 3?
Mhm.
Oh, because it's,
Yeah.
it's
Okay, so which of the functions in 1 through 4 would have a following number line? I feel like we don't have 1 through 4. Oh, I think we're missing 1 through 4. Okay, so we can't do these questions. That's my bad. Sorry. I did not cut and paste the correct questions. Whew, that's hot. Cool. Okay. So for each problem, find the open intervals for which the function is increasing and decreasing. How do we find that if we are given a function? First derivative. So the first derivative would be 2/3 to the negative 1/3. And then don't forget to derive by the inside, which is technically 1. So we don't have to say that, but just don't forget about it. So then we have 2/3x plus 5 to the 1/3. Now what do we do with that first derivative?
You figure out what makes it not zero.
No?
You have to make a number.
Set it equal to 0. Okay, so we set it equal to 0 to find the critical numbers. Okay, so if I set that equal to 0,
The whole bottom half is just gone.
the whole bottom half is gone.
So then you just have 2.
2, 0 equals 2, but what's the x value?
Oh, I don't know.
I don't know either. Okay, so basically what's happening with this function is it's probably always increasing or always decreasing. So how are we going to figure out which one it's doing?
Plug in like a positive number and a negative number and see.
Okay, we could plug in potential x values. That would totally work. How about let's graph it?
Oh,
Let's just look at it and see what it looks like.
that's the cheap way to do it.
That kind of is a cheating way to do it, but if we have a calculator, why not?
Because it's cheap.
It's cheating. Who
Gosh.
said? There's no part that says no calculator on this. You have a calculator, I would suggest to use it.
What happens when it does say no calculator?
If it does say, then you would have to use points and see if it would be increasing. So you would only need 2 points to make that decision. So you would plug in 2 x values and see if it's going up or going down. So what do we got? Whoa. Or actually, the easier way to do that is to do a concavity test.
But we don't have the critical number.
Well, you could see it's always going to be concave up or concave down, right? So you could do the
Just derive
second
it again.
derivative. Yeah. So we had
To be
x plus 5 to the 2/3, is that right? Oh. Well, that's not always increasing or always decreasing.
I think you put it in wrong.
Oh, no, I was going wrong. No, I think we're okay. So what's happening? Actually, I think what Kindle said was right. Sorry, Kindle. What did you say?
So see what makes it 0.
So that is critical. A value that makes the denominator 0 is critical. Even though Doug would disagree with me. Right, Doug?
It's just a domain restriction.
It's a domain restriction. So it becomes, I'm going to say it becomes critical because I'm saying that it's important. But by definition, it is not a critical number. And I know Doug's going to keep arguing with me about it. But it's important for a number line, right? A domain restriction is important for a number line. Okay, so what is the one value that we're looking at?
X.
The value that x cannot be. It technically is a restriction on the derivative because it does not, the derivative at -5 does not exist. Okay, do you see how that's a sharp point?
Yeah.
Okay, so our number line is just at -5. Okay, so then we can do, what should we plug in, 0? I mean, we already looked at the graph, but let's just plug in 0 just to double check. So if we plug 0 in, remember we're plugging it into the first derivative.
It's positive.
It is positive. So positive here, and if I plugged in a negative number,
Be positive on the
such
other
as
side.
-6, it would be negative. Because remember, it decreased down and up on the graph.
Oh,
Remember we looked at
yes.
it?
He is.
Okay, so we should say it increases from -5 to infinity and decreases from -infinity to -5. That was actually a good example because that made us remember about that denominator piece. How they are, in fact, crucial. Let's call them crucial numbers, so that kind of like steps over critical.
And then, like,
Yeah,
there's a big
it's
bird
perfect.
that
Crucial numbers.
does-
Okay, open intervals for where the function is concave. How do I find concavity?
You drive it again after you drive it the first time.
Right, exactly.
And then
So
find
we
the
drive
critical
twice and set it equal to 0. Okay, so first derivative is -5x to the 4th plus 9x squared. Second derivative is -20x cubed plus 18x. Okay, so then I need to set that equal to 0 to find our crucial numbers.
Right.
So I'm going to pull greatest common factor. I'm going to pull -2x here. So that would make it 10x squared minus 9. So let's see, our crucial numbers are 0. Let's see, 9. Square root of 9/10. I don't like that number. That's very that's not nice. How should I write that? I guess I better simplify it. So if we have the square root, here, let me write it over here. Square root of 9/10. 3 square roots of 10, so yeah, so it should be 3 square roots of 10 over 10, right? So plus or minus over 10, which is going to be a little more valuable if we know the decimal value for that, if we have to do a number line test on it. So we got -3 square roots of 10 over 10. We got 0 and positive 3 square roots of 10 over 10. So what's the value of that? What's the square root of 9/10? Anybody know that off the top of their head? It's not very big. Square root 0.94. Okay, so we can use like a half. So if we plug half in to the second derivative, I'm going to look at that, the one that's in standard form, I think. So we plug in a positive 1/2. Let's just use our calculator. I feel like that's going to be the most helpful. Let's see, we got -20 times 0.5 to the 3rd plus 18 times 0.5. So we get a positive. So write that down while I'm, and then I'll plug in a negative one. So negative, okay, so we had, what was that? So negative and positive, right? And then if we plug in, we want to go on the other ends of those too. So if I plug in 1 and negative 1, right? So if I plug in negative 1, we get a negative, right?
No, you get positive.
Oh yeah, positive, excuse me. And then you get a negative if you plug in positive 1. Sheesh, okay, that was fun. So, concave up. It is concave up between negative infinity and negative 3 square roots of 10 over 10. And between 0 and 3 square roots of 10 over 10. Concave, whoops. Concave down between negative 3 square roots of 10 over 10 and 0. There, that wasn't so bad, although I didn't like that number. Minima and Maxima. Okay, so what are we looking for here? Absolute mins and max.
Extrema.
Okay, so we're looking for the max and min. Yeah, we're looking for extrema. Notice that we have an interval this time. Okay, so remember that when you have a given interval between negative 5 and 3, notice that it's not including the value of 3. That'll be interesting. You have to test those endpoints.
So you have to do like
Oh, I don't know, you're ahead of me. Oh, for negative 3?
yeah. Because usually like fraction is greater than or equal to.
Yeah.
But
I've never seen it with a... This is the first time I think we've had one where it was like that.
like
I guess we should test like a... What's that?
A limit.
Well, I think that we can...
We could test a limit as it approaches 3.
Yeah. Yeah, I think that we can test it and just see where it is and assume that at negative 2.99 that would be close to it. Right.
You could put approximate.
Right. So we can see, and hopefully what'll happen is it will not be either. And then if it is one, then we'll have to figure it out. It doesn't exist, right? So then you say it doesn't. Oh, so then okay, I see what you're saying. Yeah, because then you would just need the, yeah, okay. Okay, so we're gonna derive.
I don't know if I do it. Sent it to you.
So 1/5 times 5/3 is 1/3.
No, I erased it.
And then if we subtract 3, that would be 2/3. Minus 4/3 x plus 3 to the negative 1/3 minus 0.
That's crazy.
That is not nice. So if we set that equal to 0, we're looking at yeah, that's going to be one of them. Because, hold on, I have to think about this. Because I think what you want to do is pull out a greatest common factor. And if you pull out the x plus 3 quantity, the biggest amount of those is 2/3. Technically, you can even pull out a 1/3 if you wanted to. Then you would have left 1 minus 4x plus 3. You pull out 1, subtract 1. Pull out 1. What is that? Negative 4/3? Well, I'm thinking like, okay, so if you pull out a greatest common factor, you're pulling out the most amount of that quantity. So if you compare 2/3 and 1/3, 2/3 is the most. So if I pull that out, then I'm technically subtracting off the exponent. So on the first term, I pulled everything off. On the second term, I'm left with a 4, and then if I subtract negative 1/3 minus 1, that's negative 4/3. Does that make sense? What? Oh, I don't know. Sorry. No, wait. 2/3. Yeah, I don't know what I'm doing. You're right, because I'm used to subtracting 1 because that's how we derive. That's where my brain went with that. So that you're right, I should subtract 2/3. So it should be 1/3 minus 2/3, which is just negative 1. Oh, I like that better. That's way nicer. Okay, so then you would set each of the quantities equal to 0. So we get negative 3. That one's easy. On the second one, we have 0 is equal to 1 minus 4 over x plus 3, which is the same as 1 equals 4 over x plus 3. Not like this, no. This one's algebraically very crazy. 1. But the other thing is that if you couldn't do this algebraically, which I kind of expect that probably not very many people would be able to do this one, you could at least use your calculator and solve it. So you can use the calculator on this, so you could just type it into the calculator and hit solve. So I would expect you to be able to. Maybe not with algebraic steps. Okay, that's fine because then we can double check and make sure that we're right. So, okay, so I have to pull up my, the fancy one. This takes a little while on this tablet to pull up. No, you can do your homework that you should have done. We'll go over questions. We'll still, how far are we? How many questions do we have left?
We have like just a page left.
Oh yeah, we're like almost done. And 4 of them are graphing. Those ones are easy. And I think there might be, and don't do 33 and 34. No, wait. Yeah, don't do 33 and 34 because we haven't done definite integrals yet. I anticipated that we would have done them, but we ended up not getting there. So don't do 33 and 34 because we haven't got that far yet. Okay, well then we'll go over that on Wednesday. So like, it shouldn't take long. You should be able to do the 20, I guess that's only one time. 25 and 26, that's not too bad. Oh, did you? Who'd you hear that from? Because it's not true at all. I told you, didn't I already tell you it was 29 questions? Oh, participation.
We should just not take the final. So we have the AP
What is your
test.
semester 2 final? If we take like the AP test, we not.
We'll do a project.
We should do a Mr. Hansen.
My plan will be, it'll be like, create something for a next year's student. What is valuable that you found? I don't know. I haven't quite critiqued it, but that's the idea of what we're going to do. It'll be a project of some
You should
kind.
do a Mr. Hansen final where we just go and make like rocket cars, and then we like shoot them off. At, like,
That would be kind of fun. We could do that. It will not be a test. It might be something like that. Who knows? We did rockets one year. That was kind of fun. We could do something
rockets.
different.
We should do rockets again. I remember when we did rockets before.
And you have to do calculus to figure out how high it went.
Yeah.
Yeah, okay.
But you also can find the value instantaneously.
What?
See, that's fine.
This final?
Yeah. Like, if we have an A, you should just like.
I think it should be the other way around. If they have an A, they need to prove that A.
Oh, and if you have a B, then you don't need to prove it.
I'm a B, so I'm just screwed either way.
I think we'll just have everybody do it.
Or a group
I have a
test.
97. I think if you have an A of any sort. You can
Yeah. Clint, you still can make up those things that you missed if you so
That's what
choose.
Palmer did if you have an A-. No, I did have a 92 and above you.
Okay, somebody read me what I'm typing in. So on the calculator,
X.
Neither did I.
x, is it really x?
So I should have it.
What is the equation?
X minus 4 equals 19.
Is it a deal then?
No, everybody's taking it.
It should be. Palmer does that. Yeah.
Well, do I look like Palmer to you?
Yeah. You're a lot prettier.
I need the, oh, that was good. That was a good touch there. Not far enough though, you gotta do better than that. Okay, somebody hit me with the derivative. What is it? 0 equals, how did it go? 1/3, right? Is it 1/5 or 1?
1/3.
How do I type that in? If I type in 1/3, will it give me a fraction on it right away?
No, there's like a button. Yeah, there you go. Got it. Come on.
There you go, 1. This works really slowly on here. 1/3. And then I got a quantity of, what was it, x plus 5. Who's got it?
I don't got it on my thing.
Plus 3.
And if you think about it, Noel, you won't have to grade this.
Oh, to the two.
Oh, so it's a win.
Yeah, it is for you. I think it's pretty solid.
Oh. Well, I have a student teacher now, so it's no problem.
You?
Yeah.
I heard it was
I heard she's hot. I'll let her know. Gosh dang it. Well, you know, that is an important feature of a teacher.
No.
Okay, then what? Minus
Minus, and then it was like,
4/3?
no, minus 1 minus 4. Minus the quantity of 1 minus 4. No, that's the.
Yeah, the derivative. We're typing in the derivative. 4.
It's like, each of those has like.
X plus 3 again. To the negative 1/3?
No, just negative 1, isn't it?
Negative 1/3.
Oh.
Third. And that's it, right? And then I have to say comma. Oh, wait. Ah.
Comma X.
Comma X. Okay, so Aaron, did you see how I typed it in? So you type the equation, you just go to solve, and then you have to say comma X. Because you're solving. Right.
I always forget to put the equals 0, and that's where it's.
So it only gave me
Yeah,
1.
because 3 isn't in the domain.
Oh, you're so, well, yeah, you're right.
Negative 3 isn't in the domain.
You're right. So we're only looking at positive 1, because negative 3 isn't included. It's a restriction, or it's not differentiable at that spot, right?
But positive 1 isn't even in the interval either.
So you just have to test negative 5 and positive 1, right?
I hate it when that happens because I feel like I did all those steps for nothing.
Oh yeah, one side.
Yeah.
So only 5. So basically 5 is either a min or a max. Oh, you're. But then how do we know if it's a min or a max?
Exactly.
We have nothing else to compare it to.
We'll just say it's a max.
So it's gotta be 5.
5 is either a min or a max.
Negative 5.
Oh, this is yucky. Let's just throw 3 in there just to see what happened. So if I do 5 Oh my god, what is that even?
I think you test.
One fifth. -5 plus 3 to the 5/3. 5 plus 3 to the
I think we should just
2
graph it.
thirds minus 2. Yeah, I think so. No, enter. Jeez. -5.
Does she give you the website or?
I think the intention of this was for you to just graph it on my calculator.
Could be. Second. Plug in -3. -2. So -5 is the lower spot. So this would be a min. And then you would say no max. I'm gonna graph that just to see what it looks like.
How do you get 5.8?
I just plugged it in with my calculator.
Put like an X around.
Yeah.
Like don't clog your
Don't clog your mind.
Yeah.
Zoom 6. -5 and -3.
Did you see that?
Oh.
Zoo?
Okay.
What is zoo?
Wait.
Never learned
-5.
that.
So -3 is in max. It would have been a max spot.
You were saying we were going over like all.
And then it just goes down.
Yeah.
So like, just looks like this.
When is our, so we're taking this on Thursday?
When are we taking this final?
Thursday.
Thursday.
Oh,